Hi guys, we're continuing titrations and we're going to do a strong acid with a weak base now. So our strong acid that we're using is HCl and our weak base that we're using is NH3. And just to switch things up a little bit, we this time are going to put our base in the Erlenmeyer flask and we're going to put the acid in our burette. So here we have our ammonia, and then in the burette we have our HCl. So we're going to have kind of an inverse of an S, more like a Z curve as opposed to an S curve. So we have 8 milliliters of 10th molar NH3, and we want to find what the initial pH of that NH3 is before we add any of the HCl. So since we only have NH3 in our flask here, this is a weak base. And so how do you find the pH of a weak base? You write the dissociation equation and you write an ice chart. So let's do that. So NH3 with water partially ionizes to give NH4 plus and OH minus. We're going to do an ice chart. So this is 10th molar. Don't care about the water. 0 and 0, minus X plus X plus X, 0.1 minus X, X, and X. So this is a base, so we're going to write our Kb expression. It is the concentration of the NH4 plus times the concentration of the OH minus over the concentration of the NH3. Kb for ammonia is actually equal to Ka for acetic acid. It's a coincidence, but College Board loves to use both. So we're going to use them a lot. By the end of this chapter, you'll probably have it memorized by heart. So X, which here is the OH minus concentration, right, not the H plus, is 0.00133 molar. So we're going to find the pOH by taking negative log of that, and it is equal to 2.87. And so my pH is 14 minus 2.87, which is 11.13. We are going to construct our titration curve. So we're going to need our initial pH here. So let's go ahead and put it on our curve here. So this is going to be our pH. This is going to be our milliliters of HCl, the volume of HCl. And let's make this 2 mils for 6, 8, 12, 14, 16, 18, 20. And for our pH, let's make each box a pH of 1. So 2, 4, 6, 8, 10, 12, 14. So let's see. Initially at volume of acid equal to 0, our pH is 11.13. So probably right there. Okay, so that's our initial pH. Now let's see what happens when you start adding some HCl into your flask. So now we are going to take our ammonia and we're going to add some HCl to it. So we're going to add 2 milliliters of the HCl. And when we have an acid and a base together in a titration, they react completely. So we're going to write our reaction, and it's a 1 arrow because acid and base go to completion. So let's do that. So I'm going to take my HCl, which is H plus, because it's a strong acid, I can write it as H plus, with my ammonia, 1 arrow, and I form NH4 plus. We're going to do a BCA table here because it goes to completion. So for your equilibria, like a weak acid dissociating or something like that, you do an ice chart. For reactions that go to completion, like an acid reacting with a base together in a titration, you do a BCA table. And we usually use moles for the BCA table, so we're going to figure out our moles here. Let's look at our ammonia first. We have 8 mils of 10th molar, so that's 0.008 liters times 0.1 moles per liter. So this gives us 0.0008 moles. For our acid, we have 2 milliliters, so 0.002 liters, and it is 0.05 moles per liter. So this gives us 0.0001 moles. 0.0001 moles. And we said our ammonia is 0.0008 moles. We don't have any of this to start. So when you're doing the BCA table for a reaction that goes to completion, you check which one is your limiting reactant, which one's your excess reactant. So they are a 1-to-1 ratio. And so you are going to look and see. So this one is less, and so that's going to be your limiting reactant. So that's what's going to get used up, is 0.001 moles. So we're going to use up all of our acid. We're going to use the same amount of base, and we're going to form the same amount of our ammonium. So at the end of the reaction, we don't have any more of the HCl left over. We do have some of the ammonia left, and we formed a little bit of the ammonium ion. Don't forget to divide by your total volume so we can get molarity. So I had 2 mils of the HCl and 8 mils of my ammonia, so that's a total of 10 milliliters, 0.01 liters. So this gives us 0.07 molar. This one gives us 0.01 molar. So let's look at what we're left with. So after you do your BCA table, figure out what's left. Let's see what kind of substances are left. So we don't have any more of our acid, but we do have some ammonia, which is a weak base. We also have some ammonium ion, which is its conjugate. So we have just formed a buffer. So we have our ammonia weak base with its conjugate. And so since this is a buffer, we can find the pH by doing 2 different things. To find the pH of a buffer, you could write the dissociation equation for your weak base here, do an ice chart, just like we did here. Or you could do the Henderson-Hasselbalch. So I'm going to use the Henderson-Hasselbalch. And since it's a base, I'm going to use the basic version of the Henderson-Hasselbalch. So POH is equal to PKB plus log of the conjugate acid over the base. So that is equal to, PKB means negative log of the KB, which is negative log of 1.8 times 10 to the negative 5th, plus log of, my conjugate acid is my ammonium, which is 0.01 molar. My base is 0.07 molar, the ammonia. And so I get my POH to be 3.90 is what I got. And so my pH is 14 minus that. And so that is 10.10. And so that's my pH. So after 2 milliliters, my pH is 10.0. Okay? Let's look at an animation for what is happening with this one. So I'm going to go ahead and show my slideshow here. So I have 8 milliliters of 10th molar ammonia. That's equivalent to 0.0008 moles, like we saw. So I'm going to use 0.0001 mole is one of these, and so I have 8 of them. I'm going to add 2 milliliters of my, I'm sorry, this should say HCl. I apologize. There's my HCl here. And so if I have 2 milliliters of 0.05 molar of the HCl, that's equivalent to 0.0001 moles, like we saw. And so I'm going to just release one of these. So when I do that, my H plus from my HCl combines with NH3 to form NH4 plus. And then the Cl minus is just floating around. It's a spectator ion. It doesn't really do anything. And so what I'm left with in the flask here, of course, I have some water, right? I have some Cl minuses. So both the water and the Cl minuses are neutral. They don't really contribute to anything. But I also have some ammonia left, lots of ammonia left. And I have some ammonium as well. So I have ammonia and ammonium, weak base, and its conjugate, and so that's basically a buffer. And so to find the pH of a buffer, you either do a Henderson-Hasselbalch or you do the weak base dissociation and an ice chart for it. Okay, let's look at what happens when we add more. So here it's telling us what volume of HCl is required to neutralize the NH3. And what will the pH at the equivalence point be? So normally, they just tell you, hey, we have this certain amount of HCl that we've added, calculate the pH, and, that's it. But this time, they're not even giving us the volume. They're telling us find the volume. But they are telling us that we are at the equivalence point. So what do we do? Well, as always, if you have a titration, acid, and a base, write the equation for what's happening. So let's do that. So I'm going to go ahead and write my equation. I have my H pluses reacting with my ammonia. One arrow, because this is an acid-base reaction, I form NH4 plus. I'm going to write a BCA table. And in my BCA table, I know that my ammonia is what I started out with, which is 0.0008 moles, right? I don't have any ammonium. I don't have the volume of the HCl to know how many moles. But what else do I know? I know it's at the equivalence point. Well, what do I know about the equivalence point? So at the equivalence point, there's no limiting reactant, right? All the acid and base are used up. And so for a 1-to-1 ratio, the moles of acid are going to equal to the moles of base, right? If I need to use both of them up, then there is no limiting reactant. There's no excess reactant. Both of them have to be used up. And so if I start with 0.008 moles here, that means I also have 0.0008 moles here. Okay, and that is going to help me figure out what volume of HCl I'm going to use. But I'll do that in a second. So let's do this. So we're going to use both of them up. So we're going to use up 0.0008 moles of each, and we're going to form 0.0008 moles of the ammonium. So at the end of the reaction, I have no acid, no base. I do have some of that conjugate left, though. Okay, so how do I know the concentration of my ammonium that's left? Well, I need to find what the total volume is, which means I need to find the volume of the HCl, which is what they're asking for, right? So how do I do that? Well, I know the moles of acid that I used, and I also know the concentration, so I can figure out what my volume is. So you can use the molarity equation, and so it is 0.05 molar is equal to 0.0008 moles over X liters. And so if you solve for this, you get 16 milliliters or 0.016 liters of HCl. And so my total volume would be 8 milliliters of the ammonia plus 16 milliliters of the HCl, so that's 24 mils, which is 0.024 liters. So I'm going to divide that by 0.024 liters. This gives me it's a third, right? So 0.0333 molar. Okay, so we got the answer to the first question, the volume of the HCl. The second question is, what is the pH? So to find out the pH, you do your BCA table, which we just did, And then you look, what are you left with? Well, I'm left with only the ammonium ion. Is ammonium ion neutral? No, it's not. It's not neutral. It can undergo hydrolysis. So that's how we're going to find the pH, by writing the hydrolysis equation, doing an ice chart, and using that to find our pH. So let's do that. So we're going to write the hydrolysis of my ammonium, because that's what's left. So I react this with water. This is an equilibrium. Hydrolysis is an equilibrium. Does not go to completion. I get NH3 and H3O plus. I'm going to do an ice chart. I got that this is 0.033 molar. Don't care about the water, 0 and 0. Some of it undergoes hydrolysis. Same amount is formed of these. So 0.033 minus X, X, and X. This is acidic because it's forming H3O plus. So I'm going to write the Ka expression. It is equal to the concentration of the ammonia times the concentration of the H plus or H3O plus, whichever you prefer, over the ammonium ion concentration. To find the Ka, if it's not given to you, you say that Ka times Kb is equal to Kw. We have Kb for ammonia. We know Kw, so we can solve for Ka. When you do that, you get 5.6 times 10 to the negative 10th. That is equal to X times X over 0.033 minus X. X in this case is the H plus concentration. H plus is the same thing as H3O plus, right? And I got that my X is 4.3 times 10 to the negative 6 molar. And so my pH is negative log of that, which is 5.36. Does that make sense? Yes, it does, because this is a strong acid with a weak base. And so at the end of your reaction, you have an ion that undergoes hydrolysis to give off H pluses, and so your pH at the equivalence point is going to be below 7. Let's look at this one here. So we said it takes 16 milliliters of the HCl to reach the equivalence point. I apologize again, this should say HCl here. We're using HCl. So I have 0.008 moles of my ammonia, so 8 of these, and I'm going to use 0.008 moles of my HCl, so I'm going to use 8 of these, and we'll see what happens. So here's the first one, second one, third, fourth, 5, 6, and the 8th. So what are we left with? Well, it looks like we have, of course, water, because this is happening in water. We have some Cl minuses. Water and Cl minuses don't really affect the pH, right? They're neutral. And look at this. All we have left is just ammonium, just NH4+. So how do you find the pH of NH4+? You do the hydrolysis and an ice chart. And your pH is going to be below 7 because NH4+ will undergo hydrolysis to give off H pluses. So your pH will be lower than 7. So let's go back to this here and see if we can find some other points that we can plot. So we can definitely mark the equivalence point. It's at 16 mils and the pH is 5.36. So let's do that. 16 milliliters. 5.36, so right there. We can also actually add 2 more data points to our sketch here. So this was our initial, I'm going to mark it here. We can find the pH at half the neutralization point, half the equivalence point, right? So the equivalence point was reached when we had 16 milliliters of acid. And so at 8 milliliters, that's going to be half our equivalence point, and at half the equivalence point, the pH is equal to pKa, or the pOH is equal to the pKb. And so let's do that real quick. So pOH is equal to the pKb. So pOH is going to be negative log of 1.8 times 10 to the negative fifth, which is let me calculate that real quick. It is 4.74. And so if I want the pH, it's going to be 14 minus that, which is 9.26. And so at 8 mils, I'm going to go and mark 9.26. So this point is where it's half a neutralization point. pOH equals to pKb, or pH is equal to pKa. We said this is our equivalence point right here. This is our initial one more point that you can find is the final pH. So when you draw your curve, what does it approach? And so if you keep adding HCl, add and add and add and add more and more and more HCl, eventually the whole thing will be pretty much HCl. And so it's going to eventually approach what the pH would be if you just had the HCl by itself. And so our HCl here is 0.05 molar. So if we take negative log of that, pH of only HCl would be equal to negative log of the 0.05 molar, which is, I think, 1.3. So this is the ending pH. That's what it's going to approach. So we're going to eventually get to somewhere here. So now let's draw our curve. So I'm sorry, I'm not very good at drawing, but it kind of looks like that. You can see, because this is strong, this is a little bit sharper, and this is weak, so it's a little bit curvier here.